Alright, we're going to carry on with our study of chemical change, and what we're going to look at now is an important concept, which is the conservation of atoms and mass. You know, hopefully, from somewhere along the line that, for example, energy is always conserved. Okay, so energy cannot be created or destroyed, it's simply transferred from one form to another. Mass is very similar, and in particular when it comes to chemical reactions, this mass is very important. So, the law says to us, and you can give it to me anyway, the total mass of the particles before a chemical reaction and the total mass of the particles after a chemical reaction remains constant. Sometimes that's difficult to see because maybe a gas evaporates, but the total mass always stays the same. During a chemical or physical change, the sum of the masses of the reactants are what we put in, is equal to the sum of the masses of the products. The products are what we get out. We can't lose anything. So if I put in 3 atoms of oxygen and 4 atoms of hydrogen, when I get to the end, I must still have 3 atoms of oxygen and 4 atoms of hydrogen. No matter how they've rearranged themselves, no matter what I get at the end, it's always got to be the same. So, as an equation, the number of atoms, why we balance equations, okay, must be equal on both sides. The total mass must be equal on both sides. So, let's look at the following balanced, you've done balancing before, balanced chemical reaction. So we have 2 sulfur dioxides plus 1 oxygen, which becomes 2 sulfur trioxides. So now what we're going to prove is 1, that it's balanced, and 2, that the law of conservation of mass works. So, I'm going to go to my periodic table, and I'm going to find the relative atomic mass of sulfur dioxide. That's the mass number. So if I go on my periodic table, the mass number of sulfur is 32. There are 2 oxygens, so I multiply the mass number of oxygen, which is 16 by 2, and I get a total of 64. I'm not putting a unit because this is relative, it's the scale. Then I'm going to work out the relative mass of oxygen. Well, oxygen is diatomic, we know that, and we've just seen that oxygen's mass is 16, so it's 32. Okay, let's look at the total mass before. Well, we have 2 SO2s, each SO2 is 64, so 2 times 64 plus the 32, and I get 128, which is 160. That's before the arrow. After the arrow, we have sulfur trioxide. Sulfur's 32, oxygen 16, and there's 3 of them, so it's 32, which is 180, plus 48, which is 180. But the total mass afterwards is 2 times that, because there's 2 SO3s. Oh, look, we get 160. What does that tell me? Total mass before equals total mass after. That's why we have to have a balanced equation. Always. If an equation is balanced, it means that we have the same number of each atom on both sides. It doesn't matter how they've rearranged themselves. And it means if I work out the total mass before the reaction happens and the total mass, atomic mass after the reaction happens, I get the same number. We're all happy. Good. So you would need to do activity 3. Let's now move on to law of constant composition. You have done this. This just looks a little different. It says a specific chemical compound always consists of the same elements in exactly the same ratio. Its writing formulae can only be done in a certain way. So for example, carbon dioxide is always 1 carbon for every 2 oxygens. If it's not that, then it's something else. Ammonia is always 1 nitrogen with 3 hydrogens. Carbon monoxide, 1, 1. Water, H2O, 2 hydrogens, 1 oxygen. It's the way we write formulae. Okay, it's not an option. So, practice writing formulae, activity 2, page 137.